For an extended period, humans have envisioned what existence might be like on other worlds. Thanks to the James Webb Space Telescope, the most advanced telescope currently available, that inquiry can finally be investigated. While examining the nearest star system to us, Proxima Centauri, located only 4 light-years away, scientists have detected some unusual phenomena from one of the planets in the system, Proxima B. These phenomena, referred to as artificial light, have baffled the foremost thinkers in the scientific community. But what do they signify? Do these lights imply the presence of intelligent life on the planet? Join us as we delve into the James Webb's alarming discovery of city lights that could transform everything. The only life we currently recognize is on Earth. Since the dawn of civilization, people have pondered whether life exists elsewhere in the cosmos. To undertake such an interstellar inquiry, American astronomers Jill Tarter and Thomas Pearson initiated the search for extraterrestrial intelligence, SETI project in 1984. The nonprofit's aim is to capture space-originating radio signals. Radio waves can travel further and are therefore more likely to be detected by the 42 radio telescopes that comprise the unique Allen Telescope Array in the Californian Cascade Mountains. However, in the past 3 decades, no verifiable alien signal has been uncovered. Subsequently, the successful launch of the James Webb Space Telescope has bolstered the quest to investigate a variety of undiscovered planets orbiting distant stars. As the largest telescope in existence, stationed roughly 1 million miles from Earth and equipped with highly sensitive detectors, it has the potential to reveal significant findings. 2 decades ago, no known planets existed outside our solar system, but since then, over 4,000 exoplanets have been identified orbiting other stars. According to NASA, the universe may house trillions of exoplanets. The earliest indicators of life beyond our solar system might lie in extraterrestrial plant life. The Galileo spacecraft, en route to Jupiter, turned its instruments back toward Earth and detected a clear sign of plant presence, identifying the vegetation red edge, VRE, biosignature, a mix of red and infrared lights reflected by plants. For example, a planet like Earth, enveloped in a jungle, should emit a robust and easily recognizable V signal. The JWST will assess the V of distant, Earth-like planets in the habitable zone around stars, which could provide crucial signs of life in the exoplanet atmosphere. When sunlight crosses a planet's star, the JWST may be capable of detecting it as it enters the planet's atmosphere. The missing wavelengths would then be revealed through spectroscopy as atoms and molecules in the atmosphere absorb specific wavelengths, creating a distinctive fingerprint that the JWST can identify. This technique may be employed to ascertain the composition of the atmosphere and whether life is feasible. Life could exist on Earth-sized planets with atmospheres akin to our own, characterized by a predominance of oxygen, nitrogen, and carbon dioxide. By searching for elements that are not typically found, one might be able to identify technological life. For instance, chlorofluorocarbons, CFCs, produced for refrigeration and cleaning products, would likely be detectable by aliens monitoring Earth's atmosphere from a distance. If the JWST were to find CFCs in planetary atmospheres, that would serve as a clear indication of civilization. However, life on exoplanets may not resemble life on Earth at all. Sometimes even earthly organisms like extremophiles, species that can survive in conditions where other living things would perish, can appear alien. This group of organisms, primarily bacteria, can endure extreme environments such as heat exceeding 250 degrees Fahrenheit or strong acid with pH levels below 3. Since planets like Earth are more likely to support life than those with extreme temperatures or acidic conditions, it could be prudent to start with those first. Prime candidates could possess temperatures that allow liquid water to exist on their surfaces and orbit a stable star. Our Sun is categorized as a yellow G-type star. These stars are less prevalent and typically have shorter lifespans. However, in our universe, the likelihood of studying planets orbiting red dwarf stars, which are more common and have lower luminosities and temperatures than the Sun, is higher. This extended time frame permits the formation of life and evolution to yield complex life forms. Approximately 40 light-years from Earth, the TRAPPIST-1 planetary system will be the focus of the JWST's first mission. It revolves around a calm red dwarf star with 7 Earth-sized rocky planets. 3 of these rocky planets, located in the so-called habitable zone, might possess liquid water on their surfaces. Despite its smaller and colder mass compared to our Sun, the TRAPPIST-1 star radiates light similar to that of Earth. Due to the close orbit of its planets, the best chance for humans to observe city lights outside the solar system is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun. Proxima is about 600 times dimmer than the Sun, so a planet must be 20 times nearer to it than Earth is to the Sun to support life based on liquid water. In August 2016, astronomers identified a planet with 1.3 Earth masses in this habitable region, a Goldilocks-like zone, where the light intensity is just right for melting water. Proxima B orbits Proxima Centauri, but it is possible that Proxima B is an airless, lifeless planet. Given that it circles its red dwarf star at a distance of only 4.6 million miles, this close orbit exposes it to powerful solar winds that can completely obliterate its atmosphere. However, Proxima B does receive sufficient sunlight for temperatures and liquid water comparable to those on Earth. Due to its close proximity to the star, Proxima B is thought to be tidally locked, always showing the same face to the star, much like the Moon does in relation to Earth. Proxima Centauri has about 18% of the mass of the Sun and burns far less brightly than one might expect for a planet so near to its star, just 5% of the Earth's distance from the Sun. It may appear to be a red-hot ember. Liquid water could exist on Proxima B, as long as the planet has an atmosphere to retain heat. Since the total energy it receives from the Sun is only 65% of what Earth absorbs, the planet is not particularly hospitable to life. It is most likely tidally locked, meaning it always faces the same direction toward the star, producing permanent day and night sides with significant temperature fluctuations. The planet also receives 100 times more high-energy radiation than Earth does, including X-rays and ultraviolet light, due to its proximity to Proxima Centauri. Proxima B is also bombarded with high-energy particles during stellar flare-ups. Unless it possesses a shielding magnetic field akin to Earth's, the conditions for life may not be favorable. Certain plausible circumstances could make Proxima B a more inviting world. Models indicate that the atmosphere of tidally locked planets might be susceptible to swift collapse due to the condensation of volatile gases on the night side. Nonetheless, Proxima B is likely not very hospitable to life. Being tidally locked means it experiences extreme temperature differences between its perpetual day and night sides. Additionally, the planet is bombarded with 100 times more high-energy radiation than Earth, including harmful X-rays and ultraviolet light. The frequent flare-ups from its star further expose Proxima B to high-energy particles, raising the stakes for any potential life. Without a protective magnetic field, conditions might be too harsh for life to thrive. There are scenarios that could make Proxima B more life-friendly, but models indicate that the atmosphere of tidally locked planets could collapse quickly due to the freezing of volatile gases on the dark side. While Earth replenishes its atmosphere through volcanic activity, we currently lack information about Proxima B's geological activity or magnetic field strength, leaving us uncertain about its atmospheric conditions. The presence of both an atmosphere and bodies of water would be key indicators of potential life. There's a possibility that Proxima B could utilize solar panels on its day side to generate power, enabling it to warm and light up the night side, which might otherwise be too cold for habitation. The discovery of Proxima B has sparked interest in determining whether the planet transits in front of its star as seen from Earth. Such transits would help scientists measure its size and mass, allowing for an assessment of its density and composition. During a transit, light from the star could also provide insights into the planet's atmosphere. However, the chances of observing such a transit are just 1.5%, complicated further by the star's flaring activity. Astronomer David Kipping notes that the heat from the star makes it challenging to assess a rocky planet's characteristics. Although rocky planets produce unique infrared signatures detectable by instruments like the James Webb Space Telescope, JWST, the infrared signature from Proxima B will be critical in identifying any potential atmosphere. Moreover, the JWST could detect artificial lighting if it falls within a frequency band that is 1,000 times narrower than the star's light. Proxima B's day side might be covered in reflective solar panels. As the planet orbits its star, its day and night sides will remain constant. Although the temperature differences between them depend on the planet's surface composition, an atmosphere and ocean would help moderate temperatures, while a lack of atmosphere could lead to significant temperature extremes. If there is minimal temperature variation between day and night, it could suggest the presence of an atmosphere. Fortunately, the JWST only needs about 11.2 Earth days to analyze the infrared radiation from both sides of Proxima B after completing its orbit. If the planet has an atmosphere, the next step would involve studying its composition. Detection of gases like oxygen, water vapor, and methane could hint at conditions suitable for life. However, capturing starlight that either reflects off or passes through the atmosphere is a complex task. The JWST can only focus on a select few nearby, potentially habitable worlds. Since it was not designed specifically for the search for extraterrestrial life, its capabilities in monitoring changes in methane, carbon dioxide, and water vapor concentrations are also limited, and it cannot detect free oxygen, which is a strong indicator of life. Some gas combinations might suggest biological activity, but future ground-based observatories, like the extremely large telescope, set to begin operations in the mid-2020s, may provide more detailed atmospheric studies. The JWST could potentially identify ozone as one of the gases in Proxima B's atmosphere. Until these observatories come online, the JWST may offer insights worth pondering over the next decade. Future telescopes could employ innovative methods to block the glare of a host star, revealing light reflected from planets, similar to shading a light to see objects better. These telescopes might use small internal masks or large external devices to accomplish this. Once the starlight is obscured, analyzing the reflected light from a planet becomes significantly easier. Unfortunately, many gases associated with life can also be produced through non-biological processes. For example, methane is released by both cattle and volcanic activity, while photosynthesis converts water into oxygen and hydrogen. Astronomers may encounter numerous false positives in the search for extraterrestrial life, making it crucial to understand a target planet's geology and atmospheric processes to differentiate between genuine biosignatures and non-biological origins. The next wave of planetary research may yield substantial evidence regarding life beyond Earth. The preliminary data from the JWST is just the beginning of what could be significant advancements in this field. If life exists elsewhere, it raises profound scientific questions. We might discover that life is common in the universe, or we could find ourselves completely alone, leading to major philosophical and psychological shifts for humanity. The search for extraterrestrial life has intrigued people for centuries, sparking numerous theories and narratives. As our technology evolves, our understanding of the universe expands, revealing new possibilities for life beyond Earth. Telescopes like the JWST enhance our ability to detect distant planets and analyze their atmospheres, helping scientists identify potential biosignatures. Additionally, the exploration of exoplanets encourages international collaboration in space research, fostering knowledge sharing and resource pooling that increases the likelihood of groundbreaking discoveries. These collaborative endeavors also boost public interest and engagement in space exploration, with findings often shared widely to spark curiosity and imagination. Moreover, the philosophical implications of discovering extraterrestrial life prompt deep reflections on our existence. Would finding alien civilizations reshape our understanding of life's purpose? Such questions challenge us to reconsider our role in the universe and our relationship with Earth. As we refine our technologies for exploring the cosmos, each discovery brings us closer to answering the age-old question: are we alone in the universe? The journey ahead is filled with potential, driving the quest for knowledge and understanding beyond our earthly limits.